Welcome everybody to this really wonderful and special occasion. Thank you for coming. We'll slowly on get started. So this is a joint hosted lecture between NIST, the Institute of Science and Technology for Humanity, and SPMS. Yes, I am new here well, I can't say I'm new, I've been here for a few months now, but the acronyms are really tripping me up still, so apologies for that. Also, this has been co-hosted by the Italian Embassy, so welcome. And we will hear a little bit more from you. Let's see, today's talk is very special. We'll hear a little bit more about Professor Maiano's background, and for NIST, it's really an honor that he is here, a wonderful honor. And because everything that happens in this, I would want to say, fundamental science, in basic science, it's at CERN, really has a lot of impact also on society. To get to the point of real fundamental science, a lot of other things have to be invented too, that kind of drop out and end up being really beneficial for many aspects of society. So it's really really wonderful to look at the larger picture today, to get an idea of what is happening, where we are going, how this impacts our world, hopefully for the better. And to start with that, maybe the attaché of the Italian Embassy would like to tell us a little bit more about the background. So you have been attaché since 2019.
I'm quite new like you, yeah.
Quite new.
We're both new in Singapore, yes.
Okay, so we are both new in Singapore,
yeah,
but
we're very excited to be here.
We are very excited to be here. So I will leave you to it. Thank you.
Thanks a lot. Okay, so my name is Nicola Bianchi. I'm scientific attaché of the Italian Embassy here in Singapore, and it's a great pleasure to have invited here Professor Luciano Maiani. Luciano Maiani was born in Rome, in Italy, and he got his university degree in Roma, La Sapienza, which by chance is also my university. And he got also many other doctor honoris causas from many universities in the world, like in Marseille, France, St. Petersburg, Russia, Bratislava, Slovakia, Warsaw, Poland, and Puebla, Mexico. And now he's emeritus professor of Roma University La Sapienza, and he has been awarded many, many international prizes. As a theoretical physicist, Luciano is worldwide known for the famous GIM effect, where G stands for the Nobel laureate Glashow, E for Heliopoulos, and M for Maiani, where they postulate the existence of a new kind of subatomic particles, the charged particles. These particles, after their prediction, were really discovered after a few years, and a Nobel Prize was awarded for this discovery. He developed a lot of new theory in the Higgs boson. Maybe some of you have heard about this new discovery, on supersymmetry, on quantum chromodynamics, and on exotic hadrons. And who of you is more in this kind of issue and is more interested? You are invited to the seminar of Luciano that will be held in NUS University on Friday at Department of Physics of NUS at 10:30. Will be more really on physics. Well, Luciano Maiani is not well known just for his fundamental research in basic science and physics, but I think also because his effort to manage and promote science, not just physics, all over Italy, all over Europe, and all over the world. So in Italy, for example, he was leading many government institutions, just mention a couple, the INFN, that the Institute for Nuclear Physics, and the CNR, that is a National Research Council. And these two institutes cover a broad range of research, not just physics, but also geology or material science, astrophysics, biochemistry, and so on. And according to the last Nature Index, both INFN and CNR are among the top 10 government institutions all over the world with respect to the number of publications. And this also thanks to the leading effort of Luciano. At a more international level, he chairs a lot of international committees. I just want to mention one that I like a lot because also was partially involved in this, is the UNESCO International Center for Theoretical Physics, which was founded by the Nobel laureate Abdus Salam. And the mission of the institute was to connect scientists, especially from developed countries. Just imagine that over the last 50 years, 5 decades, more than 100,000 of visitors, scientists from 170 countries came to Trieste, to this institute, just to discuss their result and to be trained in different fields of science. Just continuing on the spirit of promoting exchange of research and cooperation, that is one of the most important aspects of our work. I want to mention that Luciano Maiani, together with his wife, Veronica Riqueri, that is here, she's also a physicist from Mexico, they found two networks from Latin America and Europe, two Latin American network for exchanging researchers. And in 10-year period, thanks to them, more than 3,000 month person fellowship has been granted for exchange between 22 Latin American institutions and many institutions in Italy, France, Germany, Switzerland, and so on. Finally, since this seminar has been organized, thanks Vanessa for hosting all the organization, everything was perfect. In this new NTU Institute for Science and Technology for Humanities, I want to mention that Luciano is also now president of the International General Balsam Prize for achievement in the field of humanities, natural science, culture, and peace. Last, of course, but not least, I guess you were president and director general of CERN, something like that. But this will be the main topic of his talk, so I will not say so much about this. But, okay, since I'm representing the Italian embassy, we are waiting the ambassador. I hope he will arrive. Please forgive me if I want to be a little bold about Italian scientists, because when CERN was founded in 1954, the general director of CERN was an Italian, was Edoardo Amaldi. Now the general director of CERN is an Italian, is Fabiola Giannotti. Actually, she was the first woman who achieved this position. And the next general director of CERN will be an Italian, again Fabiola Giannotti, that few weeks ago was appointed for the second mandate. Also, this is the first time that a general director of CERN has been appointed for the second mandate. And so I think this is quite good. So we did a good job, I think. Since our ambassador is not here, maybe you can start, or maybe when he will arrive, for sure he will want to say something. You can go. Okay, thanks a lot, and enjoy the talk.
Can I?
Is it okay?
Yeah.
Fantastic.
Okay. Thank you.
So, well, many thanks. I'm very glad to be here and to tell you about CERN, this wonderful institution which was created in Europe about 60 years ago. And is it too high? Volume. It was too high. And that is a very interesting example of international collaboration. So if I can move to this. Mm-hmm. So that is a view of the banners which are outside outside CERN, and on the background there is a wonderful mountain which is the Jura mountain. I will come back to that. And I will tell you about CERN, and I would like to start with this figure, which is a sort of summary of the accelerators which are present at CERN. It's a very complicated figure, and you may think that all these are toys that have been played in the past, In fact, most of these machines do not do research anymore, and are left there just to fill up the figure. But it's not so. In fact, accelerators are like bottles. In which sense? You have to fill them with particles, and then the particles will be accelerated to higher energy. But it turns out that it is much better to fill the bottle with a smaller bottle, not directly with the particles. And so there is a line which joins this, which is the first accelerator built at CERN in 1959, to the next accelerator, which is the SPS, which was built in the 70s, to the final accelerator, which is the Large Hadron Collider I will speak about, which is here. So in fact, this complex of accelerators is kept perfectly working, and all the know-how and all the infrastructure accumulated there grows with the energy of the laboratory. So, particle accelerator, what are they? Well, somebody says are microscopes. Some other will tell you that they are telescopes. Some malignant persons say they are like the cathedrals of 20th century, meaning that they are useless to build. I don't know what to think about cathedrals, but that's what it is. Certainly they are sources of new technologies, as I will try to tell you. And as I said, they are in sequence bottles to fill one after the other. All these definitions are correct. They are microscopes. From Rutherford, at the beginning of last century, we know that if you want to study a microscopic particle, the only way is to illuminate it with some form of radiation or particle and get the details out of that. And so they are the biggest microscopes ever constructed. In fact, we know now details which are 10 to the minus 19 centimeters, which is about 1 million smaller than the size of a nucleus, of an atomic nucleus. But they are also telescopes. We can reproduce states of the matter which were present in our universe, which is 10 billion light years apart from us, so 10 billion years, in the early universe. And the cathedrals 20th century, yes, they are big projects which, like the cathedrals, attract intelligences, young people, and so on. So they serve as a coherent force to promote science. Sources of new technologies, the web, the positron electron tomography, hadrontherapy, and more. I will say something about that later. And in fact, with this battery of bottles that I illustrated here, CERN won the high energy war that developed to search for the Higgs boson that I will tell you about. But let me start with a picture which is what we all learn in school. How is matter organized? We know that we have crystals. We know crystals are made of atoms, small particles of about 100 millionth centimeters. But we know from Rutherford that the atoms have a complicated structure. We have a nucleus, which is 100,000 times smaller than the atom. In the center is the atomic nucleus and surrounded by a cloud of electrons. And we know from 1930s, and when this picture was understood, we know that the nucleus is made of smaller particles, which are protons, the nucleus of the atomic of the hydrogen, charged, and neutral particles, which are called neutrons and have been discovered in 1932. And in the same year, Fermi understood that the radioactivity, which is so characteristic in nuclei, one form of radioactivity, which is called beta radioactivity, is simply due to the disintegration of a neutron into a proton by emission of electron and a neutrino. A year after, a Japanese physicist, Hideki Yukawa, understood that the forces which keep protons and neutrons together into the nucleus are transmitted by a particle which has to have a mass about 200 times the electron mass. And this particle, since then, has a name, which is known to all of us, is our friend, is called the pi meson, and it's a universal name. So you see that this picture of the matter in the universe that goes from our dimension, or the star, or the Earth, if you want, to 10 to the minus 13 centimeters, can be interpreted in terms of very few different kinds of particles. You have 4 particles which make the matter, proton and neutron, the electron and neutrino. The electron, of course, makes the surrounding of the atom. The neutrino appears in the beta decay. And then we have 2 particles which are the glue that glue the particles together, the photon, the quantum of the electromagnetic field that makes the atoms, and the pion, which makes the nucleus. This was the picture in 1932, and to a good approximation is still a good picture, but we learn many other things. The first is that in 1937, Anderson and Neddermeyer discover a particle that is produced in the collision of cosmic rays in the upper atmosphere. I don't want to go into the detail of cosmic rays. It's simply radiation that comes from the universe, very high energy. And this particle was called mesotron because it had a mass intermediate between the electron and the proton. So it was in the middle. And in fact, its mass is close to the mass predicted by Yukawa for the pi meson. So it was understood, it was thought that the table that I had in the previous slide had been completed with the last particle to be discovered. It all looked very reasonable, but 3 young Italian physicists working in Rome, in fact, at the time where Rome was occupied by the Nazis during the last year of the war, they made a specific proof that the mesotron is not the Yukawa particle. Cannot be. And a year after, Bruno Pontecorvo, another Italian who was emigrated to the United States, understood that this particle is just a heavier copy of the electron. It's just like an electron, 200 times heavier. And it was a real surprise because it was a particle that did not belong to the scheme that I illustrated before. It's not in the atom. It's not in the nucleus. It's just produced by energy, high energy collision. In fact, a very famous physicist, Rabi, commented, who ordered that? And at the same time, in the same years, between 46 and 50, 52, 53, many new other particles emerged from cosmic ray studies. In particular, a class of particles which had very strange properties and were called the strange particles. That's a very nice name that remained with us, the strange particles. All these particles, the strange particles, the muon, etc., are not, as I said, constituents of matter in any sense. However, they are there, and we must understand what is their role in the architecture of the universe. And what was realized at the time, it was that cosmic rays are a too weak, feeble source to allow us to study all these particles, and that it was necessary to develop what I call particle accelerators, that is experiments in the lab where you produce a particle which has very high energy, similar to the primary protons in the cosmic rays, smash against a nucleus and see what happens. And then you produce many particles, and then you can study the new particles, the strange particles, the muon, and all the other particles that are there. We are now arrived just after the war, the late 40s, and Europe was in a total disaster, and all the energies have gone to the United States, which were starting a very intense program of particle accelerators. It is at this time, that Louis de Broglie, a French physicist who's one of the founders of quantum mechanics, wrote a prophetic letter by saying that Europe should make a laboratory, a common laboratory, financed by all the European states to do scientific work that could go beyond the framework of the different participating states. Nobody could afford to do these studies. And he had a very clear view that fundamental research was the realm of such an enterprise, and he said very nicely, due to the intrinsic truth of science. It's very nice. Just a year after, there was a conference of UNESCO in Florence, and Rabi, again Isidore Rabi, made a proposal. And he asked UNESCO to assist and encourage the formation of regional research centers in the search of new knowledge in fields where the effort of any country in the region is insufficient for the task. This is the message. Unite your forces and you will be able to do first-class research that no European country could do at the time. In a press conference following his talk, Rabi stated that the task was to build a large accelerator of the type which exists in the United States in such places as the MIT, Chicago, New York, and Berkeley. So in a way, Rabi is considered the father of CERN because he identified who had to do that, UNESCO, and what UNESCO had to do, a large accelerator. And CERN was, in fact, established just 2 years after Rabi talk, and the delegates to CERN sent a telegram to Rabi, which was very nice. We have just signed the agreement which constitutes the official birth of the project you fathered at Florence. Mother and child are doing well, and the doctor send you their greetings. A wonderful telegram that announces to the world that European countries have been able to overcome their differences and make a laboratory for fundamental research. Most of the task of doing this fantastic thing was done by these three people: Edoardo Maldi, who's a pupil of Enrico Fermi, who stayed in Europe and is the father of the many Europeans, Italian and European enterprises. Pierre Auger, a very famous scientist in atomic physics, and who was the UNESCO scientific director, and Leo Kowarski, who was the director of the Atomic Energy Commission of France, Commissariat de l'Énergie Atomique. And it is these people that had the vision to give substance to the prophecy of de Broglie and to the invitation of Rabi. And there is a very nice book which is called The History of CERN, which I, in fact, picked up from CERN library and steal for myself, and who give a very positive judgment on these people. Their goal was not merely to construct a medium-sized accelerator, it was to awaken Europe, and through the construction of a giant accelerator, to make her understand the urgency and necessity of developing fundamental scientific research on a large scale, as had happened in the US since the war. I think we should keep this word in mind. They apply perfectly well to our times, and we should keep this lesson very well. And in 1954, CERN was created and is now the European Laboratory for Elementary Particle Physics. CERN has 22 member states. These are 20, and then 2 members have added more recently, Israel, Romania, and etc. And as observers, associates, Turkey, Pakistan, India, Ukraine, and observers, the big nations, European Union, Japan, Russia, and USA. CERN is a laboratory where people go to work at the accelerator machines, bringing their own knowledge and their own funds, and remaining attached to their original country. These are what is called the CERN users. Every year, one makes statistics of the user. This is the last one that Fabiola Gianotti has shown very recently in Rome. And you see that the numbers are startling. There are about 8,000 physicists and engineers from the CERN member states, which are those here in blue. There are more than 1,000 from the United States, more than 1,000 from Russia, China, Japan, and then all over the place. India, a very good number, etc. CERN population is very multi-ethnic, multiracial. That's a very nice picture of some physicists of an experiment of the lab machine, which was there since a few years, of CERN. And what is more important is that CERN is made of young people, because CERN is the home of many PhD students that do their PhD with their home university, but working at CERN. So at a given time, if you make a statistics of the ages, you see a wonderful, wonderful curve, which has a peak at 27 years, and then these are the old guys, like me. They are on here. But the laboratory does not get old with the old guys, because it's replenished every year by the new PhD students that come there. And oh, sorry, I'm sorry. And I just wanted to say another things, but okay. And I want to stress that CERN is not producing brain drain. What people were used in Europe, or also in China, in your countries, is that the best people would go to the United States and would stay there, period. They are lost for your country. But CERN is not like that. These people that are here, they are students of their own universities, and they use CERN to make their PhD. And after PhD, a good fraction of them go to industry, because they can use the know-how that they have acquired in technology, etc., and others remain in research. This is a very nice transparency that Fabiola showed just 1 month ago, and with a very nice picture with Berners-Lee and the United Nations Secretary General Kofi Annan. In 2003, we celebrated the 10 years when the CERN had renounced to the royalties of the web. CERN has put the web, the World Wide Web, at disposal of the whole community. Meanwhile, there are Nobel Prizes obtained by research at CERN. So CERN can really be thought as a world laboratory with the basis of 18,000 scientists and more than 100 nationalities. Now I want to tell you another thing about accelerators. It's a concept which has been developed in my times. I saw it, the birth of it. It's called the particle colliders. The traditional method is to make what the American newspaper call atom smashers. You make a beam of particles and you smash the atom with that. Colliders are a completely new concept, which was invented, in fact, in Italy by Bruno Tuschek, an Austrian physicist who was working in Rome. He was my professor, to make instead collision in flight of a particle against a particle. He was saying train against train instead of train against wall. Much better. And relativity makes it much more useful to produce energy. But of course, it was a terribly challenging technological problem because a beam of particles is essentially vacuum. So it's very rare that they encounter. You must make beams which are very intense. You must put many, many particles in your bottle to come to the thing in order to produce collisions. And the first electron-positron ring, which was called ADA, was made by Tuschek and collaborators in 1962. And since then, the idea has developed into the largest facilities in the world. These are the previous generations: proton-antiproton, Rubio and van der Meer, proton-antiproton Tevatron, and LEP, electron-positron and CERN. I will tell you a slide about that. And then, after that, the new step into the high energy was done at CERN by the Large Hadron Collider. I will tell you in a moment. This is a nice photograph of ADA, the machine made by Tuschek in Frascati. It was about 1 meter. It could stay on this table here. This is the largest electron-positron collider ever built. It's a circle of 27 kilometer diameter, 100 meters underground, near Geneva. Geneva is here. This is the lake. These are the Alps. And on this side, there are the mountains of the Jura. This is another picture that gives you perhaps a better idea of the situation of this big circle. This is the Jura mountain, this is the lake, and this, as you see here, is the Geneva airport, that the lanes of the airport, just to give you an idea of the dimension. It's important to notice, and I will come back to that in fact LEP occupies all the space which is available between these mountains and the lake. Cannot be done larger, and that is the problem that we are going to face in the next year. So let me now come back to the picture that I had before, from crystal to nuclei. That was my picture, and with all these accelerators, including LEP, we arrived to the conclusion that in fact protons and neutrons are made of smaller particles, which Gell-Mann proposed to call quarks. It's a strange sentence taken from the Finnegan's Wake of James Joyce, in which somebody sometime says 3 quarks for Master Mark. It's not clear what quarks mean, but in fact in the proton there are 3 quarks. So that's why I think Gell-Mann chose this wonderful name that is now so famous in our business. Nuclear forces are transmitted by meson, as I said, but also by other particles, including the strange particles, etc., which are all made of quarks. They are quark, anti-quark. The particles makes nuclear forces, and 3 quarks in a proton, the quarks that make the barrier. And Gell-Mann had to introduce another quark to take care of the strange particles, the strange quark, and so, in fact, it had 3 quarks for Mastermark. Now I give you the picture which was formed about the end of the 80s, which replaced the previous picture. This is Maury-Gell-Mann. These are the quarks that he has introduced. 2 of them we call up and down, and they make all ordinary matter, as it was in my previous transparency. Then there is the electron, the neutrino, but Gell-Mann, as I said, had to introduce another quark, which he called the strange quark, because it has to explain the strange particles. And we remained for some time with 3 quarks. And this is a nice picture of Nicola Cabibbo, who was my mentor in some way, that succeeded in including the down and the strange quark into a scheme which was the extension of Fermi interaction to that. And starting from Nicola's work with Glashow and Iliopoulos, we understood that there had to be another quark, which we call the charm quark. And so 2 generations, up-down, electron-neutrino, charm-strange, muon, the mesotron of Anderson and neutrino mu. But then later on, these 2 Japanese guys, Kobayashi and Maskawa, understood that to understand completely particles, we need to have another generation, top and bottom quark and another neutrino and another lepton particle of the same kind. And in fact, this particle and this particle and this particle have been found. So we now are, with this scheme, we have produced all of them, and we know perfectly well, and we do not understand why there are no others. There seems to be finish here. Then there are the forces. The forces are mediated by the photon, electromagnetic, by 2 vector bosons, which are the weak interactions, discovered by Carlo Rubbia and hypothesized by these people, Glashow, Weinberg, and Salam, and a particle, which is called the gluon, which has to mediate the quark, the forces between quarks. So the old Yukawa picture comes back again. You have quarks. Quarks are bound by the gluon into the proton and neutron, etc., and then there are the other forces which are here. That's a wonderful thing, but there is still one thing which is missing, and is the Higgs boson. To give a mass to all these particles, you need another particle which creates the condition for this particle to acquire a mass. And that is the situation, let's say, at the end of the 80s, where we knew everything except for the Higgs boson. Now we go to the Higgs boson. I wanted to give you a picture like that to show you that finding the Higgs boson was really a long, long story. First of all, it was the Large Hadron Collider to produce the Higgs boson was proposed by Carlo Rubbia, that you see here, and the first design of this machine was done by Giorgio Brianti here, and that was 1984, more or less. But then there were other directors of CERN that succeeded Carlo. One is Chris Llewellyn-Smith, then myself, then Aymar, and so you have here 4 people, each lasting 5 years, that worked coherently to produce the machine that had to do the Higgs boson. So 20 years. But Aymar could not see the machine working because there was an accident and it took years, and the real success of the machine was in fact in a 5th director, which we will see in a moment. The art of the LHC are these very powerful magnets, because you have to keep the protons in this 27 circumference circle. You cannot change the circle because the mountain, the lake, you cannot do that. So you have to have the largest possible magnetic field, and these were the largest possible magnetic field at the time. They are superconducting magnets, 1032 to be sure, that had to be installed and are here installed into the lab tunnel. Magnets are the secret of these machines. You have this machine, these magnets, as I said, they've been produced in France, in Germany, and in Italy. And then you have other magnets called quadrupoles, which have been contributed by the United States, Fermilab. And then you have other magnets, which have been built in Novosibirsk in Russia. So it's an enormous production of magnets, which has then been assembled into this tunnel, into the machine, etc., to make this large. It was a very big industrial enterprise. LHC used 1,200 tons of superconducting cable. And for the time, in the year of construction, LHC was the largest single buyer of niobium titanium cables. In fact, it was the competitor to the large industry that made this cable for the magnetic resonance diagnostic machines. And we were competing with that, and LHC in this year was by far the largest single buyer. You start from a bar of 1 meter long and 20 centimeter diameter, and then it is extruded. That is, it is passed through a hole. You pass through a hole, then you pass through another hole, smaller hole, and you produce a filament which has 7 micron diameter and 30 kilometer length. It's a really fantastic thing, which required, now it's well known, a large technology. The magnetic prototypes have been done at CERN in collaboration with the INFN for Italy and European companies. It has been an enormous effort in collaboration between research and industry. The heart was at CERN, the industry was all over the world. Part of the niobium, the niobium titanium cables have been done in Japan, for instance. And so to say. Okay. The LHC had 4 large detectors. You see here 2 of them that were dedicated to the search of the Higgs boson. One is called Atlas. This is a very nice picture of Atlas, but you don't see, unfortunately, the man who was here. It has been reduced. There is a little man. Can you see it? Yes, here it is. This is before this is what is called the central calorimeter here. And now it is in the back, but after when this man went out, it was pushed inside this space. And these are magnets that bend the particles so that you can measure the characteristic of the particle. This is another one, very similar, which is called CMS, but C stands for compact. This was very big, this was much smaller. And this is a diagram of the jobs that have been submitted to analyze this data. I will come back on that. You can imagine that a machine like that produces enormous amount of data. You have to analyze them and find the Higgs boson inside the enormous amount of events, and that requires a computer effort, which I will discuss in a moment. Then there are 2 specialized telescopes, which are still there. All the detectors are there. They address what happened at the beginning of the universe. As I said, in the first instance after the Big Bang, quarks are unconfined, as we say. They wander and condense into proton and neutron only after the temperature has gone below some value, which appears here at about 10 to the minus 5 seconds. And you can reproduce these conditions in the collisions of heavy ion, and LHC is able to do lead-lead collision, and you can reproduce in this collision the condition of the universe which were present in the universe at the time. And also there is another one which is called LHCb, which studies the decay of the particle containing the beauty quark, which I showed you in a few slides above, and whose decays contain a signal of an asymmetry between matter and antimatter that may have produced, we don't know, the unbalance of matter versus antimatter we see in the universe. We see in the universe the stars. We know that there are stars and galaxies, but there are no anti-stars and no anti-galaxies. And that's a very strange phenomenon, which is called the baryon-antibaryon asymmetry. And we want to have information on that by this thing. That's the picture of the day, the 4th of July 2012, when the collaboration announced the observation of a boson with mass under 25 times the mass of the proton. And this is the director of the time, Rolf Hoyer, and this is Fabiola Gianotti, that was at the time the leader of Atlas, and this was the leader of CMS. And these are Peter Higgs and Robert Englert. And Robert Englert, which were present that day to the announcement of this historical discovery. The famous physicist Leon Lederman had called the Higgs boson the goddamn particle because it was so elusive. But the editor didn't like that, and he changed it into the God particle, which is much better. And the name stayed. And this is a cartoon which appeared after the discovery, which I like very much. God Almighty on line 2, he says he wants his particle back. Now, technology transfer. That's the greatest example of technology transfer of CERN. The web was invented by Tim Berners-Lee, as probably everybody knows. But what was the reason? The reason was to allow easy exchange of data between the collaborations working at lab. At that time, they exchanged data by sending fax. And they were very happy with that. They sent fax. But he understood that there was another way. That is, by internet, you could go in the site of your friend and read the documents there. And that was the invention of the web. In 1994, there was one site. We still have at CERN the server which has that, and it grew exponentially in. For LHC, I said you need even more data, and it was realized what is called the grid, which now you call the cloud. The CA system in which you transmit data and programs to the user, starting from a large storage, which is in fact distributed all over the world. Electron-positron tomography. You have a substance which emits a positron. The positron finds an electron, and they annihilate into 2 photons. And by the difference between times of arrival of the photons, you get the position of the annihilation. So you get a tomography of the tumor. And that is really something which is now very well used. What we have now is what is called knowledge transfer. At CERN today, starting from the mission of CERN to develop accelerator, detectors, training, etc., you have a list of technologies here, and you would like to transfer this technology to the society. The crucial point, the crucial point is this. Everybody who tried to do technology transfer, including myself, has found this terrible territory, which is between research and industrial development. That is what you have to develop if you want to do technology transfer. At CERN, they have a system of funding of projects which try to pass the desert between research and industry. And they have startups, a system of startups now distributed all over Europe, and that is the idea of that. I think I will stop here, and if you want, I can tell you about the future in the future slides. Thank you very much.
Thank you so much. Thank you so much, Professor Maiani. I'm sure that I speak for everybody that we could listen for another 2 hours. It's been so fascinating. It's so compelling. It's such an adventure that you've been on, and to share that with us is really wonderful. So the time is just simply too short to do this. For those who have to leave at the allotted time of 5:30, we will understand if you need to move out. If it's still possible, we'll do a little Q&A for people who would really like to speak with you. Before we start that, I would want to ask the ambassador of Italy to have maybe a short reflection, since you are the embassy invited Professor Maiani here.
Thanks a lot. I mean, I know we are running short of time, and I could entertain you for hours talking about Higgs bosons and so on. The only Higgs boson I know is the Higgs boson blues by Tom Waits and the Bad Seeds. I mean, if you don't know the song, I mean, go home and listen to it. I just wanted to thank Professor Maiani. I mean, we met some 20 years ago in Geneva. I was working for the Italian representation to WTO, and it's been a pleasure to meet him again here, so far away from Europe. Of course, to thank Nicola Bianchi from the Embassy of Italy, who arranged everything, the NTU for hosting us today, and you all, of course, for being present here today and to share with us this quite interesting moment together with Professor Maiani. Thanks a lot. Thank you very much.
Thank you so much. Okay, we'll have a brief Q&A, if that's possible. Yes. So I'm sure there are many questions to ask. This is our chance, I guess, to ask a few questions. Is there anybody in the audience who would want to start, or is it too intimidating? Oh, you have? I'm back.
My name is Jørgen Slund. I'm in food science, food safety here, microbiology. We actually have some ideas globally to try to create something which would be a little bit similar to CERN, where we try to create a database in the cloud of all DNA sequences of all microorganisms in the world. I'm sure that will happen maybe in 50 years' time. We're just saying we should have it in 20 years' time. But in relation to that, what is the total budget of CERN? Because the total budget of CERN.
So ordinary to speak of money.
Well, in a way, it's difficult to say, but the mission of CERN is to make research in particle physics, okay? But of course, doing that, you discover that there are technologies that you have to develop for that, and they will never be developed by industry. Take the web, for instance. Okay? Microsoft did not think about. So research is a source of technology that then can be transferred to society. And I think this is certainly one important reason. The other reason is the other social effort of CERN is to put together people of different countries in an experiment which has no, as I said, brain drain. You are not taking out brains out of less developed countries, or Europe for that matter. They are still there, but they can do first order, first level research. This would never be happening if you have research concentrated in few centers in other places. So I think this is, I try to explain that. I think these are the main reasons why European countries continue to finance CERN.
And so the question was how much they finance it.
How much?
How much? Yeah, you may not want to answer it, but
You mean what is the budget? Well, CERN has a budget which has been essentially constant over the years since LEP, since the previous machine. It's around 1,000 million Swiss francs, 1 billion Swiss francs. Fabiola says 1.2, so they increase it. But part of that comes from extra contribution. So, but that is the amount of thing. And as Fabiola likes to say, is like one cappuccino per year for every citizen in Europe.
not that much. I think we have time for one short question, if there is any.
But there is one slide that I want to show you,
Okay, go ahead. Let's do that.
which has to do with the challenges. I will go fast, so let's.
I can see some
This we
hesitance.
can
So you
come
guys
back
want to
on.
ask something, but you're not sure? Feel free.
What's next? There are several projects next, but I want to concentrate on these 3 slides. The most promising project to go to higher energy, where we suspect that our wonderful picture will be still modified in a substantial way, is to make a circular tunnel, but much larger, of the order of, say, 100 kilometers, and put there a machine, an electron-positron machine, which may produce Higgs bosons in large quantities, so that we can study their properties and detect from their properties the next step to do. Then, exactly as we did at CERN, you could put into this tunnel a proton-proton collider, which would go to an energy which is about 10 times the energy of the LHC, and that will explore the region where we think there should be various things. Now, the interesting point is that not only CERN is thinking about that, but China is also thinking to come into the game. That is the novelty of the last years. There is a study which says where there can be sites where to put this thing. One of these sites is here, near Shanghai, in Changsha, which is the place where the ceramics which are in the Tang wreck were made about 1,000 years ago. So it would be very nice. There are studies about that. The idea is, this is the CERN idea. As I said, the LHC is in a tunnel which is between the lake and the mountains. To enlarge that, you will have to do a completely different design, a tunnel which goes around this mountain here, the Jura, the Salève, and then goes below the lake. That's very difficult. Of course, in China, there are no difficulties of finding places where you have a tunnel of 100 kilometers. One of those places is Chengdu, who is this one. Don't ask me to say that. Is the where the big wall starts. It's near Beijing here. And of course, it's a fantastic challenge, which will imply very new technologies in material science, low temperature, electronics, computing, big data, artificial intelligence, whatever you want. And we hope that this can be realized to solve the hardest scientific problem which we have been confronted in the last 100 years, that is, what is the picture of the elementary particles? Thank you very much.
It's so wonderful. Let's hope that's possible. Everybody puts in one more cappuccino,
Sorry?
and let's hope this is possible. Everybody pays one more cappuccino when we're able to realize this.
One more cappuccino.
And hopefully you will come back to tell us more about it. Thank you so much.